Today we are going to do the second session of the chapter Solid State. See, in this particular session, we will be talking about electrical properties and magnetic properties. So first, let's talk about electrical properties. We all know that the electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. So 1s2, 2s2, 2p6, 3s1. See, in a sample of sodium, the sodium atoms are at very close proximity to each other. So instead of having discrete energies, each orbital, like for example 1s orbital has got a range of energy like this. Similarly, 2s orbital has a range of energy like this, 2p orbital has range of energy like this. So each orbital has got a range of energy rather than discrete energy. That is because the sodium atoms are at close proximity to each other and therefore they influence each other's energy levels. Now suppose this is the energy band of 3s orbital. Now you will notice one thing, that I have half shaded it. So this half shaded portion, this implies what we call valence band. And just above it, the half empty portion, this implies conduction band. So 1s, 2s, 2p, 3s. 3s is half filled, so that half filled portion is the valence band, and the half empty portion just above it is conduction band. These two bands are so close to each other that at ordinary temperature, due to a small electric field or due to thermal energy, these electrons can easily go to conduction band. Once the electrons go to conduction band, they become free electrons, mobile electrons, and therefore they are capable of conduction. So this is the energy diagram for sodium. Now let's have a look at the energy diagram for zinc. See, in case of zinc, the configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So in case of zinc, what happens? You will see that the 4s energy band is fully filled. The 4s energy band is fully filled. And this 4s band is the valence band. And the 4p band is completely empty, that is the conduction band. These two bands, they are found to overlap with each other. So unlike sodium, where 3s band is half filled, that is valence band, and the rest is conduction band, here the 4s band is the valence band and 4p is the conduction band, and they have an overlap. So that means in case of good conductors like sodium or zinc, either the valence and conduction band are very close to each other or they have an overlap. In either case, you will get lot of conduction or lot of free electrons, and that is precisely why we say metals are good conductors. Now, if you look at diamond, see in diamond, this is the valence band, this is the conduction band, and there is a huge gap between both of them. So at ordinary temperature, it is impossible for a valence band electron to go to the conduction band. The only way it can be done is by inducing or applying a potential difference of more than 1,000,000 volts. That potential difference can cause the valence band electrons to go to conduction band. Otherwise, there will always be a huge gap, and that is precisely why we say that substances like diamond are insulators. Now suppose you consider a semiconductor like silicon. In a semiconductor like silicon, what happens is that the valence band and conduction band are neither very close nor overlapping, and at the same time they are also not as far apart as in diamond. In fact, they are much closer. So a small fraction of valence band electrons can acquire enough energy to go to conduction band. So there will be some electrons, but that will be a small fraction. Let's understand this particular phenomenon a little better. Suppose you have a structure of silicon. So you will find that each silicon atom is surrounded tetrahedrally by 4 neighboring silicon atoms. So every silicon atom has 4 neighboring silicon atoms, and these are the covalent bonds between the two. Like between these two, this is a covalent bond. Between these two, this is a covalent bond. Between these two, this is a bond, like that. Now in each bond, I have shown 2 lines. So these 2 lines stands for 2 electrons. Now suppose let us say that one of the electrons, it leaves the valence band and gets promoted to conduction band. So if this electron gets promoted to conduction band, then what will happen is this electron will become available for conduction. At the same time, there is a possibility that because there has been a vacancy created, there is a possibility that another neighboring electron may leave its bond and go and occupy the vacancy created by this electron. So we say like this, that you have got one electron and one vacancy. A vacancy is also called a hole. So in semiconductors, you will always get pairs of electrons and holes. Silicon is called an intrinsic semiconductor. So intrinsic semiconduction is the semiconduction associated with the natural form of that particular element, like silicon. But remember what I said, that the fraction of electrons which are coming out of the valence band will be very, very low. So to increase the number of electron hole pairs, what you can do is you can add an impurity to the silicon. You can add an impurity to the silicon, like you can add a pentavalent impurity like phosphorus. So you know that phosphorus is pentavalent. So there are 4 bonds with 4 silicons, but phosphorus has got a 5th electron. So that 5th electron will revolve around the nucleus with a very, very large orbit, and practically we can consider that to be a conduction electron. So such a semiconductor is called a N-type semiconductor because the conduction is due to the majority carriers, which are the electrons. The other thing which we can do is we can add a trivalent impurity, like for example, if we add aluminium is a trivalent impurity. So if you add a trivalent impurity, then there will be 3 bonds of aluminium with 3 silicons, and at the site of the 4th bond there will be a vacancy because aluminium has only 3 electrons in the outer shell. So this vacancy, as we all know, that it is a hole, and because all the bonds are equivalent, there is a possibility that one of the electrons of any neighboring bond will come out and occupy this place. So that possibility is there, and when that happens, we say that the hole has moved from here to here. So this is again another example where adding an impurity has increased the conductivity, and such a semiconductor is called p-type because the holes are equivalent to positive charge, because hole is nothing but absence of electron. So it is known as a p-type semiconductor. And this entire process of adding aluminium or phosphorus, this entire process is known as doping. So this is the topic, electrical properties of semiconductors. Now we move on to the next topic, that is magnetic properties of semiconductors. First of all, let's understand one thing, that an electron in motion is basically a charge in motion. So an electron basically revolves around the nucleus and it also spins on its axis. So somewhat like the motion of the earth around the sun. So there is a revolutionary motion and there is also a rotatory motion. So either way, an electron in motion is a charge in motion, and every charge in motion has an associated magnetic field. Now what happens is that there is a category of substances known as diamagnetic. So in diamagnetic substances, what happens, that all electrons are in pairs. So in diamagnetic substances, all the electrons are in pair. So because all the electrons are in pairs, therefore they don't have any net magnetism, because for every pair of electrons, the magnetism cancels out. So there is no net magnetism. Say for example, this is a diamagnetic substance, and initially of course you can see that it is completely non-magnetic. Now you apply an external magnetic field to this diamagnetic substance. Each atom which is having a net magnetism can be substituted by a dipole. Every atom of an element or a material which is basically having a net magnetism can be substituted by a magnetic dipole. So you represent it with an arrow. The arrowhead is the north and the other one is the south. So if you apply a magnetic field to a diamagnetic substance, what will happen? That dipoles will be induced in such a way that they will oppose this external magnetic field. So this is the action of a diamagnetic substance. So diamagnetic substance, you can have a lot of examples like H2O, NaCl, C6H6, all these are examples of diamagnetic substances. Next we come to paramagnetic substances. In case of paramagnetic substances, what happens? Each atomic dipole can be represented by an arrow like this. Now what you do is, if you apply an external field, you will find that the atomic dipoles will align themselves perfectly according to the external field. So initially the dipole alignment is a little random, but it becomes perfectly aligned after an external field is applied. And examples of paramagnetic substances: oxygen Cu2 plus, Fe3 plus, chromium 3 plus, etc. These are all examples of paramagnetic substances. Next we come to ferromagnetic substances. Now in ferromagnetic substances, what happens? The dipole alignment is pretty strong even before we apply the external field. But after applying the external field, it becomes further strengthened. And the example of ferromagnetic substances is iron, cobalt, nickel, then gadolinium and chromium oxide. So these are all examples of ferromagnetic substances. Next we come to antiferro. Antiferromagnetic substance. In this one, what happens? The dipoles are oriented oppositely and cancel out each other's magnetism. So when you apply a field like these two are all aligned towards the right, but these two and these two are aligned towards the left. So in anti-ferromagnetic substances, there is a ferromagnetism, but the dipole alignment cancels out in pairs. And example of that is manganese oxide. Then we come to the next example, that is ferrimagnetism. In ferrimagnetism, what happens? It is again a type of ferromagnetism, but the dipole alignment direction is in unequal numbers. Like you will see, majority of them are aligned towards the right, but few of them are also aligned towards the left. And examples are Fe3O4, MgFe2O4, and ZnFe2O4. So these are the different examples of ferrimagnetism. So this completes the topic magnetic properties, and it also brings us to an end of the second session of the chapter solid state.